Ladies and gentlemen, good evening. So this will be the last part from the last chapter number 6, Eigenvalues and Eigenvectors. In this lecture, we will talk about diagonalization problem. In fact, we will be interested in two things in this lecture. We will be interested in finding the eigenvalues of similar matrices and determine whether a matrix is diagonalizable or not. And if it is, then we want to find the diagonal matrix. And also, we'll be interested in the same thing for a linear transformation. To find a linear transformation and a basis B for which a T relative to that basis is diagonal. Okay, so let's get started. Fortunately, I have written the notes are already written, so we can go faster. But first we will be talking about the diagonalization problem. And the problem that we pose is the following. This is the question that we want to answer, which says that for a square matrix A, does there exist an invertible matrix P such that P inverse times AP is diagonal? That is the question we want to answer. Well, and let me recall what from previous lecture what it means for two matrices to be similar. So two square matrices A and B are similar if there exists an invertible matrix P such that B can be expressed as P inverse times AP, right? So this is what we said from last time, from last lecture. This must happen. Well, we will see that when we, we have seen, in fact, that if a matrix A is similar to B, then B is also similar to A, right? So that's the definition. And now we want to point out that matrices that are similar to diagonal matrices are called diagonalizable. And now let's let's give the definition for a diagonalizable matrix. So an n by n matrix A is diagonalizable when A is similar to a diagonal matrix. That is, A is diagonalizable when there exists an invertible matrix P such that P inverse times AP is a diagonal matrix. This is very, very important. Right? So that's the definition. And now, in what will follow, we will give some examples of matrices that can be diagonalized. But before that, we above definition, the diagonalization problem can be stated as, well, we want to answer which matrices are diagonalizable. This is the natural question to ask. Well, and a partial answer, clearly every diagonal matrix D is diagonalizable, because you can write according to the definition above. As you can see, we can take P to be the identity. Clearly, the identity matrix is invertible, right? So let me remind you that the identity matrix is that matrix that has 1 on the main diagonal and 0 in rest. Well, definitely, you can write any diagonal matrix as the identity inverse times the D times the identity. And now let's give some examples. So this is the this is the definition. And now keep in mind the definition. And I want to give some examples now. And let's start with example number 1. I think we have seen this matrix before in a different context. A 3 by 3 matrix. So the matrix A is given by 1, 3. On the first row, it's 1, 3, 0. On the second row, 3, 1, 0. And then on the third row is 0, 0, negative 2. Again, a 3 by 3. And we say that A is diagonalizable because there exists this matrix P. We have previously seen this such that, and of course, this matrix P, I'll leave it to you as an exercise to prove that it's invertible. Well, you can just compute the determinant. Well, it's not hard to see that the determinant is non-zero. And moreover, if we multiply the inverse, I think we have written the inverse in some previous lecture, and we multiply this by A and P, you will get this diagonal matrix. And as you can see, well, we will see a theorem that something happens with these elements on the main diagonal. As you can see, the diagonal matrix has 4, -2, and -2 on the main diagonal and 0 on the rest. So we want to have this guy, we want to make this guy to look as simple as possible. Why not diagonal? So that's the purpose. Okay, so that's the first example. And also there was another example, but anyway, we'll go there. But before, let me say a few words about similar matrices. And there is a theorem which probably you might expect, that if A and B are two n-by-n similar matrices, then they have the same eigenvalues. In other words, they have the same characteristic polynomial, they have the same trace, they have the same determinant, you name it. So it's not quite unexpected for this not to happen. And now let's give another example. Let's consider the following two similar matrices. Look at them. So I consider the matrix A to be this 3 by 3 matrix. The first row has the entries 1, 0, 0. The second row has the entries -1, 1, and 1. And the third row, -1, -2, and 4, right? And now we consider this very nice diagonal matrix D. As you can see on the main diagonal, there are the elements 1, 2, 3, and then the rest of the elements are 0. And now what we want to do here is to find the eigenvalues of my matrix A. Well, since I have a huge start here, look at the statement, consider the following two similar matrices. Well, it's quite clear what the eigenvalues are. Well, let me point out something here. Well, you can do it, you can find the eigenvalues of the matrix A by proceeding in the traditional way, by just writing the characteristic polynomial. You set it equal to 0, and then you find the eigenvalues. So since you have a matrix of order 3, you might expect to have at most 3 eigenvalues. Anyway, some of them might have, you might have 1 eigenvalue with multiplicity 3. Anyway, it doesn't matter, but you will have at most 3 eigenvalues. Like I said, you can do it in a traditional way. But now, since I look at the statement in this case, and I want to find the eigenvalues of my matrix A, look what it says. It says, consider two similar matrices, A and D. So maybe, since these are similar, so maybe I can express somehow, there will be maybe there is an invertible matrix P, right? I'm playing basically the definition since I know what similar is, such that D equals P inverse times AP. And moreover, D will have the eigenvalues of A on the main diagonal. Wow, that will be a huge thing. And guess what? This is exactly what happens. Well, let's look at D first. Let's analyze D because it's a very simple matrix. It's the diagonal matrix. We can say everything we want about this diagonal matrix. Since D is diagonal, the eigenvalues of a diagonal matrix are exactly the elements on the main diagonal. In our case, we have lambda 1 equals 1, lambda 2 equals 2, and lambda 3 equals 3. These are the eigenvalues for D. But who knows, maybe they're the same for A as well. Well, we know that A and D are similar, and by the definition, basically, we know that this implies that, well, by the above theorem, I don't need to use the definition, this implies that A and D, they have the same eigenvalues, right? Just look at the above theorem. Two similar matrices have the same eigenvalues, that's it. Since I know that A and D are similar, I know what are the eigenvalues of D are, then I know what the eigenvalues of A are without even writing the characteristic polynomial, and that's it. Therefore, the eigenvalues of A are lambda 1 equals 1, lambda 2 equals 2, and lambda 3 equals 3. End of story. Now let's point out a remark. Like I said, you can check this if you want to convince yourself that these are indeed the eigenvalues of the matrix A. You can just proceed by showing that the characteristic polynomial, right, has roots 1, 2, and 3. And indeed, if you want to compute the characteristic polynomial of the matrix A, indeed it will be lambda minus 1 times lambda minus 2 times lambda minus 3. And I will leave it to you as an exercise to show that this is actually true. It's just a computation, so I'll skip it. Now we have the following important theorem, very important theorem, because it will give us a necessary and a sufficient condition for a matrix, for an n by n matrix to be diagonalizable. The theorem states the following. An n by n matrix A is diagonalizable if and only if, as you can see, it has n linearly independent eigenvectors. Very important theorem. And the key result, like I said, I'm not going to dwell too much on the proof, but in the proof of this, which is important, we have to look for the key point in the proof of this theorem. The key result in the proof is the following fact for diagonalizable matrices. And this is important. This fact is very, very important. The columns of P, well, as you can see, if we take the implication from left to right, we know that A is diagonalizable, so therefore there exists a matrix, an invertible matrix P, such that P inverse times A times P is a matrix D, which is diagonal. So the columns of that matrix P in the if you write the multiplication P inverse times A times P, and as you will see that matrix P will consist of n linearly independent eigenvectors. That's very, very important. So that's the key result in the proof of this. So like I said, a diagonalizable matrix implies that there exists a matrix P invertible such that P inverse times AP is D, where D is diagonal. Okay, so let's look at this theorem again. Let's keep it in mind because I'm going to use it. Well, also I'm going to use a version of it, a consequence of this. And now let's see an example. Let's look at this matrix. Again, I'm going to take the same matrix, right, from the beginning. So let's go back to example number 1. Again, this matrix, the entries are 1, 3, 0, 3, 1, 0, and 0, 0, negative 2. And we have seen that this matrix has eigenvalues. We've actually seen a few lectures ago that the eigenvalues and their corresponding eigenvectors are the following. It has 3 eigenvalues, 3 distinct well, 2 of them are the same. It has lambda 1 equals 4, and its corresponding eigenvector is 1, 1, 0. Lambda 2 is negative 2, and the corresponding vector to this will be P2 is 1, negative 1, 0. And again, for lambda 3 equals 2, -2, right? It will have a corresponding eigenvector 0, 0, 1, right? So these are the, of course, the matrix P, whose columns correspond to these eigenvectors, so I'll look at these eigenvectors here, right? This, and this. So I'll put these as the matrix P will be formed by these, the eigenvectors as columns. So as you can see, P1 is here, P2 is here, P3 is here. So 1, 1, 0, 1, negative 1, 0, and 0, 0, 1. So that's my matrix P. Moreover, P is row equivalent to the identity matrix. So the eigenvectors P1, P2, P3 are linearly independent. Or you can just say that the matrix P is invertible, and that's enough. So you can just compute the determinant to show that it's not 0. But in any case, the eigenvectors P1, P2, P3 are linearly independent, right? Now let's see the second example. Let's look again at this 3 by 3 matrix given by 1, 0, 0, negative 1, 1, 1, and the third row, the elements, the entries on the third row are given by negative 1, negative 2, and 4. Okay, again, we have seen that this matrix A has eigenvalues and their corresponding eigenvectors given by the following. So lambda 1 equals 1, and its corresponding eigenvector is P1. So again, this is the corresponding eigenvector for lambda 1 equals 1. For lambda 2 equals 2, we have P2 is 0, 1, 1. This is the corresponding eigenvector. And for lambda 3 equals 3, we have the corresponding eigenvector P3 equals 0, 1, 2. Again, we form the matrix whose columns correspond to these eigenvectors, and it will be given by this. So this is P1 here, P2, and P3. Again, P is row equivalent to the identity matrix, so the eigenvectors are linearly independent, right? Right, it's the same story. And now I'm going to give you some steps for diagonalizing a square matrix. This is very important. This is how we diagonalize a matrix. Step 1. But first, let's consider an n by n matrix, A. And now step 1 is the following. We find n linearly independent eigenvectors, let's say P1, P2, P3, Pn for A, if possible, with corresponding eigenvalues lambda 1, lambda 2, and lambda n. So this is what we find first. We find the eigenvalues and their corresponding eigenvectors. If n linearly independent eigenvectors do not exist, then we can simply conclude that the matrix A is not diagonalizable, so we can stop there. But if the n linearly independent eigenvectors do exist, then we can go to the step number 2, which says the following. We form this matrix P, just like we have seen in these examples. So we consider this matrix P the n by n matrix whose columns consist of these eigenvectors. In other words, we form our matrix P is given by this guy here. Look at it, right? Where P1, P2, Pn are the columns, right? The eigenvectors as columns. So we form this matrix, which will be an n by n matrix. Well, guess what? It will be invertible, so there will be no problem. And step number 3 is the following. The diagonal matrix that we see here, D, which is P inverse times AP, will have the eigenvalues lambda 1, lambda 2, lambda n on its main diagonal. So this matrix has these eigenvalues on its main diagonal. And now I want to point out something, a remark here. Note that the order of the eigenvalues used to form P will determine the order in which the eigenvalues appear on the main diagonal of D. Pay attention, this is very important. So if you consider lambda 1 to be, it doesn't matter the order, but make sure you would put, if you consider, I don't know, lambda 1 equals 2, and lambda 2 equals 0, and then lambda 3 is 100, then make sure you take into account the order that in which the eigenvalues appear on the main diagonal of the matrix D. Okay, let's see an example. Let's look at this problem. Example number 1. So in this, we want to see how we diagonalize a matrix. But before we see how to diagonalize a matrix, let's show that the matrix A is indeed diagonalizable. Well, the matrix A is a 3 by 3 matrix given by the following entries. So on the first row, we have 1, negative 1, negative 1. On the second row, we have 1, 3, 1. And on the third row, we have negative 3, 1, and 1. We want to show that this is diagonalizable. Okay, so it's quite clear what we need to do. And then also, we want to find this matrix P, this invertible matrix P, such that P inverse times AP is diagonal. Okay, let's get started. First of all, before we even start, we need to write a characteristic polynomial. We need to find the eigenvalues and then their corresponding eigenvectors, and then we'll form the matrix P. Let's see. So firstly, we write a characteristic polynomial, and as you can see here, the characteristic polynomial is the determinant of lambda I minus lambda times the identity minus A. Sometimes people just write the other way around, but anyway, since this is a 3 by 3 matrix, well, it's just going to be a negative sign in front of it. You can write the determinant of A minus lambda I, and you take a minus outside of the determinant. Anyway, it doesn't really matter that much. And when you compute this, the determinant, I know this will be like an exercise for you when I've done the computation, so I don't want to waste time in writing those. This will be, the characteristic polynomial will be given by this guy here. Is lambda minus 2 times lambda plus 2 times lambda minus 3. Well, clearly, we will have 3 distinct eigenvalues. So the eigenvalues will be lambda 1 equals 2, lambda 2 equals negative 2, and lambda 3 equals 3. And now, for each eigenvalue, we'll find the corresponding eigenvector. Okay. Let's see. Well, for lambda 2 equals 1, equals 2, sorry, we just look at this matrix, 2 times the identity minus A, which is this matrix. And then by elementary row operations, we reduce this matrix to this one, 1, 0, 1, 0, 1, 0, 0, 0, 0, right? And the eigenvector here, when you try to get the solution of the system, it will be negative 1, 0, 1. So this will be the corresponding eigenvector for lambda 1 equals 2. Then guess what? The same story will apply, the exact same story will apply for the second eigenvalue. Lambda 2 equals negative 2. We will have negative 2 times the identity minus A, so which will look like this, as you can see it. Negative 3, 1, 1, negative 1, negative 5, negative 1, 3, negative 1, negative 1. And again, by row elementary operations, and I'll leave this to you as exercises, we will obtain the following row echelon form, echelon matrix: 1, 0, negative 1, fourth, 0, 1, 1, fourth, 0, 0, 0. And the eigenvector, well, after we solve the system, is given by 1, negative 1, and 4. And finally, For the last, for my last eigenvalue, lambda 3 equals 3, we do the same thing. So our matrix 3 times the identity minus A, which is given by the matrix that you see, 2, 1, 1, negative 1, 0, negative 1, 3, negative 1, 4. And again, by row elementary operations, this will row reduce to the following matrix: 1, 0, 1, 0, 1, negative 1, and 0, 0, 0. And again, the eigenvector for this will be negative 1, 1, and 1. Okay, we have found the eigenvalues and their corresponding eigenvectors. Okay, great. And now, guess what? We look at these eigenvectors and we form the matrix P, whose columns are the eigenvectors that we just obtained. This matrix P looks like this: and negative 1, 1, negative 1 for the entries on the first row. The entries on the second row are 0, negative 1, 1. And finally, on the third row, we have 1, 4, and 1. Clearly, this matrix is invertible. I'll leave it to you as an exercise to show this. It's just a matter of computations. You can just compute the determinant, and you will see that it's non-zero, which implies that it is invertible. And also, moreover, it implies that the eigenvectors are linearly independent, and therefore A is diagonalizable. So we have proven that A is diagonalizable, and now we're trying to find the diagonal form. And one can show the way we find the diagonal form, we just find the inverse of this. And one can show, well, I'm going to skip those computations, I'm sure you can do them, that P inverse times AP would look like this. And as you can see, this matrix, this diagonal matrix, this is what we want. That's like a dream come true, to have, to do this kind of operations in such way that the resulting matrix will be diagonal, which happens in this case. We obtain this diagonal matrix, and the elements on the diagonal are 2, negative 2, and 3, and the rest are 0, right? So we diagonalize the matrix. We show that it's diagonal, and this is its diagonal form. And now let's see another example. I'm going to consider now a 4x4 matrix. And again, the same thing. I want to show that A is diagonalizable. And P inverse times AP is that we want to find a matrix P such that P inverse times AP is diagonal. Okay, let's look at this problem a bit. Okay, again, the same thing. We need to find the eigenvalues and their corresponding eigenvectors. Well, the eigenvalues are lambda 1 equals 1, lambda 2 equals 2, lambda 3 equals 3. Right? Okay. And we need to find their corresponding eigenvectors. Well, their corresponding eigenvectors, I'm just going to say it directly. For lambda 1 equals 1, this will have, it will be we'll have multiplicity 2, so we'll have 2 corresponding eigenvectors, as you can see them here. These 2. Then for the second eigenvalues, for lambda 2 equals 2, I'll have this corresponding eigenvector, as you can see it here. Right? And finally, for the third eigenvalue, lambda 3 equals 3, I'll have this corresponding eigenvector. Look, these are the 4 eigenvectors. Again, I'll form a 4x4 matrix whose columns consist of these eigenvectors. There we go. It's this matrix P. So this matrix will consist of its columns will consist of the eigenvectors that we just found. Okay, so this is the matrix. It's a 4x4 matrix. I'll leave it to you as an exercise to show that this is invertible. So since this is invertible, clearly A is diagonalizable, and moreover, if we multiply P inverse times AP, it will give us this matrix. 1, 1, 2, 3. And guess what? These are exactly the eigenvalues that we have already found. So this is the diagonal matrix. Let's call this D. Right? It's a 4x4. Like I said, the elements on the main diagonal are the eigenvalues of A. Well, that's not quite unexpected. And the rest of the elements are 0. Okay, that's the problem. Now let's see another example. I want to see an example of a matrix that's not diagonalizable. And this time I'm going to take a 2x2 matrix. Look at it. So it is the matrix that has the entries 1, 2, and 0, 1. We want to show that this is not diagonalizable. Well, guess what will happen? This matrix has something in particular. It's a triangular matrix. Well, since it's a triangular matrix, the eigenvalues are exactly the elements on the main diagonal. And guess what? The eigenvalues, we have only one eigenvalue, lambda equals 1. And this eigenvalue will have multiplicity 2. So as you can see, if we want to find the corresponding eigenvector, we just take 1 times the identity minus A, which is this matrix. And I'll leave it to you as an exercise to show that its row-reduced echelon form matrix will look like this. Well, this will imply, if we want to find the solution, will imply that x2 is 0 and x1 is t, with t some real number, and then we can write the corresponding eigenvector of A as this one here. So it's t times the vector 1, 0. Well, as you can see, clearly A does not have two linearly independent vectors. So A is not diagonalizable. And that's the end of story for this. So you have seen an example of a matrix which is not diagonalizable. And now we have the following theorem, which I think clears up everything at this point. Yeah. And this is a very, very important theorem. And we'll see some examples how to use this theorem. This theorem says the following: if an n by n matrix A has n distinct eigenvalues, then the corresponding eigenvectors are linearly independent and A is diagonalizable. Wow. In other words, I have a n by n matrix, and I know that it has n distinct eigenvalues, then clearly their corresponding eigenvectors are linearly independent and clearly A is diagonalizable. In fact, in the second part of the review session, I will use this result to relate the eigenvalues of a matrix to the determinant of A or to the trace of A. We will see a proof of this using this result, as well as the other results that I just mentioned earlier. Let's see an example. Let's also leave the theorem so that we can see both. The example is the following. We want to determine whether this matrix, and this matrix looks very nice, it's a triangular matrix. And as you can see, the elements on the main diagonal are 1, 0, negative 3. And the elements below the diagonal are 0. And we want to show that this is diagonalizable. Okay, clearly, like I said, A is triangular, so we know the eigenvalues. So the eigenvalues are this, right? So we have three distinct eigenvalues, lambda 1 equals 1, lambda 2 is 0, and lambda 3 is -3. And moreover, these eigenvalues are distinct, so A is diagonalizable. That's it. So by the above theorem, that's it. We don't need to prove anything. We know that this is diagonalizable. Well, of course, to find the diagonal, to write this matrix in the diagonal form, well, that's another story. And now we pose the following question: how can we state the diagonal? We want to translate the same story to linear transformation. So we want to say, how can we state the diagonalization problem for linear transformations? And for in other words, given a linear transformation T from vector space V to V, does there exist a basis B such that the matrix for T relative to that basis is diagonal? That is the question we want to answer. Right? And now let's see an example. I'm going to give you an example. So I will consider this following linear transformation. T from R3 to R3. T of x1, x2, x3 is given by x1 minus x2 minus x3, x1 plus 3x2 plus x3, and the third coordinate is given by -3x1 plus x2 minus x3, right? And now, if possible, find a basis B for R3 such that the matrix for T relative to this basis B is diagonal. Okay. Well, we usually do, we write a standard matrix for the linear transformation T, which is given by this. You just look by the coefficients of the linear transformation, and you put them on as rows on the matrix A. So that's how we write the standard matrix. It's 1, -1, 1, -1. Then the second row is 1, 3, 1. And the last row, the third row, the elements are -3, 1, and -1. Well, clearly A is diagonalizable. We have this fact about A is diagonalizable. The basis for my linear transformations will consist of these vectors: -1, 0, 1, 1, -1, 4, and -1, 1, 1. So the matrix for T relative to this basis is given by this guy here, D, which will be this diagonal matrix, and the elements on the main diagonal are given by 2, -2, and 3. And that's it. Well, we know this, we have seen previously that this matrix here, this 3 by 3 matrix, is diagonalizable and so on. So we know this from a previous example that we have seen. Okay, so this is the story. This wraps up everything about diagonalization. Well, more or less, there will be also the orthogonal diagonalization, but that's another story. I think for this chapter of eigenvalues and eigenvectors, it will be sufficient. Okay, thank you very much. I will stop here.